Hey y'all, we're going to review some things on graphs, and let's start with domain and range. On this first graph, we just have random points plotted. To find the domain and range, we can't box it in because the graph is not continuous. This graph is discrete. So let's actually identify all of these points. This is -4, 2. This one is -2, -1. Then we have 0, -2, and 2, -1. And then 4, 2. Now, since this is all of the information we have about the points for our domain, we simply need to list the x's. And it's the x's because domain always refers to the x's. So everywhere you see a domain, go ahead and write an x to it, next to it. That tells me the range is always referring to the y's. Okay, so to write our domain, we're going to start with a squiggly line, which is called a bracket, and an x, and then a line that means such that. And these points tell us the only possible values of x. So since there are only these possible values of x, we can write x equals because there's only a few possibilities. X could equal -4, -2, 0, 2, or 4. And then our range is going to be similar. Our range are simply the y values. So we start with the squiggle or the bracket, y such that y equals -2, -1, and 2. We do not need to list multiples. So even though we have this -1 and this -1, if we cover it once, we don't have to cover it again. So that's how we would do domain and range of a discrete graph. But on number 2, we have a continuous graph. So we're going to do it a little bit differently. We need to box this graph in. So let's go ahead and box in the left side. Notice on the left side you have a solid dot. So let's draw a solid line through that left side. Now on the right side we have an open dot. And because our dot is open, we need to draw a dotted line through that side to show that open dot. Now, if we look at the top of this function, we have a solid dot and a solid line. So we should draw a solid line. Now, if we look at the bottom of the function, we have this open dot and a solid line on the same spot. A solid line always fills in everything, so we're going to draw a solid line, not open, even though you have that dot. Okay, so now let's look at our domain. Our domain again is the x's, so we're going to look at where your box touches the x-axis, which is here and here, at -4 and 8. But if we look at our graph, there's all these x's in the middle that it goes with as well. So our domain will look a little bit different, but it starts the same. It starts with your squiggle, your x, your such that. Now this time when we have two special numbers, we're going to write them on the outsides and put your x in the middle with two inequalities. This is showing that we start at -4, there's more x's in the middle, just like you have this x in the middle, and then you end at 8, just like this ends at 8. Now let's look at our signs. At -4, we had a solid line, which means it could be equal. And at 8, we have a dotted line, which means it's not equal, and we leave it like it is. Now our range is going to be with the y, so let's look at where our box touches the y-axis, which is here at -2 and here at +2. So we're going to do the same thing as before. We'll have our -2 on one side, our 2 on the other, and our y in the middle, and our signs. Now again, this is telling us on our graph we start at -2 just like we start at -2 in our range. Then as we go up, there's all of these other y values in the middle, just like you have your y in the middle. And then there's this 2 that we stop at. It doesn't go past 2, so we stop at 2 here. Now at -2, we have a solid line, so our inequality can be equal. And at +2, we have a solid line, so our inequality can be equal. And that's how we do domain and range for that kind of question. Now number 3, again, is a little bit different. It is continuous, so we should box it. Now if we box the left side on this arrow, we're going to mess up the picture because we know arrows continue on forever, and that arrow would break through our box. So I cannot box in the left side. Similarly, I can't do the right side or the top, but I can box in the bottom. Okay, so our domain is the x's. Let's find where our box crosses the x-axis. Well, our graph crosses the x-axis, but our box does not. Since our box never crosses the x-axis, our domain is all real numbers. Now what this is really saying, since your arrow is going to the left forever and to the right forever, you're touching all of the x's on the x-axis. You're going to have x values everywhere. So we just put all real numbers because we can't box in those x's since our arrows keep going. Now let's look at the range. We need to find where our box touches the y-axis. It looks like it touches the y-axis at -2. So we can use our normal squiggle, our bracket, our y such that. Now this time we only have one number to compare to y, so we need to be clever. Our graph starts at -2, all right, we have a -2, and then it grows upwards. As we grow upwards, we see that the y's are getting bigger. Now since our y's are bigger, that means our inequality should be eating the y, or we should have a greater than symbol because the y's are getting greater than -2. But notice they're also equal to -2. There's one spot where it's equal, and then the rest are greater than -2. And that's your range. Now you guys tend to like number 4 a lot, because if you notice, we can't box this one in anywhere. The arrows just keep going forever and ever to the left, to the right, to the top, to the bottom. Now, since I can't box it in at all, that leaves both my domain and my range as all reals. So we can write it like that, or you could use this double bar R, which means all real numbers. Okay, now let's look at number 5. Our domain is my x's, the range is your y's. Now, let's see about boxing this continuous function in. I can't box the top, I can't box the bottom, I can't really box the left or the right, so I'm going to have to be clever here. My domain is the x's. Now let's look at this. What is the x value for this point? Well, I notice x equals 1 there. On this point, well, x still equals 1. X still equals 1. So here, my only possible x values are 1. So I'm going to write that in my domain. X such that x equals 1. I don't need an inequality because on this line, the only possible x values are 1, so I'm exactly equal. Now on my range for my y values, they're all changing. I'm here at -6, -4, -2, +2, +4, and I keep going forever and ever in both directions, which tells me again, I have all real numbers. All right. So number 6, we have our domain goes with the x's, our range goes with the y's. And let's box this in if possible. Can I box the left side? Well, I guess so. There are no arrows to break through. And I notice I have an open circle, so that means I need to draw a dotted line. On the right side, I have a solid circle, so that means I need to draw a solid line. Domain again deals with my x's, so I want to find where my box crosses the x-axis. Looks like it crosses it at -2 and +3. So my domain is x such that, and if I look at my graph, I start at -2, my x's keep going up, all the way to 3, and that's where they stop. Now let's double check. I have an open line here. Okay, it's not equal. I have a solid line, so my inequality at 3 should be equal. Now let's look at our range. Well, our range really isn't changing. It looks like my y values are all the same. And it looks like all of my y values are -6. So my range is y such that y equals -6 because it's not changing. All of those y's go with -6. Okay, so that's a quick and dirty refresher on domain and range. Let's look at parent functions now. There are 2 parent functions you will learn about this year. There are plenty more, but you will only learn about 2. And one of them is called the linear parent function, which is y equals x. Well, notice y and x are the same, so in this table, all of these numbers should be the same. So -2, -1, 0, 1, 2, 3. Now if I plot these points, I'm going to make a nice pretty little line like this. Now I could keep going, but I don't want to. So let's go ahead and draw an arrow through this. And because I can indeed keep going, make sure you draw your line with arrows on the end to show that this line keeps on going. Some important characteristics to notice here is that it goes through the origin. If I can write for you. Your linear parent function makes a straight line. And all x values equal the y values. And then for our domain and range, we cannot box it in anywhere because of those silly arrows, so our domain is all reals. And our range is all reals. Great. Let's go ahead and turn over to the next page. Now we have a quadratic parent function, y equals x squared. To fill out the table for this, since you have a y equals equation, you could very easily put this in your calculator. To put it in your calculator, you first need to click y equals, clear out whatever's in there, and put in your x squared. Now to find the table, notice in blue, we have table written here, so you're going to put second, and then table, and we can copy that table onto our paper. So we have 9, 4, 1, 0, 1, 4, and 9. Let's go ahead and plot these points. And then connect it with a nice curve with arrows on the end. Because if you notice in your table, there are plenty other points we could plot, but we don't want to, so we put arrows to show that. So some things to notice about this quadratic parent function is that it creates a U shape. It goes through the origin. It's symmetric about the y-axis. And that just tells us that it's the same on both sides of the y-axis. So this section, if I folded it on top of the other one, would be the same. And it is continuous. Well, it doesn't always have to be. Let's leave it there. So our domain here is our x's. So I want to box in whatever I can. I can't box the left or the right or the top, but I see that I can box the bottom with a solid line because it's all closed circles. Well, notice your graph is going forever and ever in the left direction and the right direction, just like your x-axis. which tells me my domain is all reals. Now my range, my y's, I notice I stop down here at y equals 0, but I continue forever and ever up. So my range is y such that all of my y's are bigger or equal to 0. Okay, let's use this information to identify certain kinds of graphs. So we're going to determine if these functions are linear, quadratic, or neither. If they're linear, they should look like a line. If they're quadratic, they should have a U shape. And if they're neither, well, they don't have either of those. Number 9 looks like a line, so it's linear. Number 10 looks like a U shape, so it's quadratic. Now number 11, even though it's curvy, it is not the U shape, so it is neither. All right, finally, number 12. Now we don't have pictures, and we need to determine if they're linear, a line, quadratic, the U shape, or neither. But notice on A, B, and C, we all have a y equals. Well, if you have y equals, let's just take that and throw it in our calculator. So let's go to y equals and put in this fraction. You can either put in the fraction using the shortcut or put it in parentheses. It truly does not matter. Now to look at a picture, graph it. Now I notice this makes a nice, pretty line, so that tells me this function is linear. All right, let's try the next one. We have y equals, let's clear out what we have, 2x cubed plus 3x squared minus x. Let's graph it. That is a very difficult thing to see. It's really hard for me to tell if that's a line. I'm not so sure. So what I'm going to do is I'm going to zoom in. I press zoom, and now I'm going to go down to zoom in, press enter, and enter one more time. Oh, that is definitely not a line, and it has 2 u's. So that looks to me like it is not linear, and it is not quadratic, so it is neither. All right, finally the last one. We have y equals 2x plus 5 plus 2x. All right, let's graph it and see what we have. That looks like a line, so that must be linear. Great. Let's turn over and see what else we have. Okay, so now we have some situation graphs. With situation graphs, they can get pretty tricky, but if you break it down into each piece that's happening, you should be okay. So number 13, we have a train pulling into a station and letting off passengers. Now, if you look at all A, B, C, and D, they're all comparing speed and time. So let's think about a train when it pulls into a station. When a train pulls into a station, it is going to slow down. Its speed will slow down, decrease to a stop. If it does not stop fully, the passengers are going to have to jump off and hurt themselves, and they don't want that. So A and B are gone because these trains never actually stop. Now D doesn't make sense because this train never slows down, and that would be quite scary. So that leaves us with C. Okay, let's look at the next one. 14, a man takes a ride on a Ferris wheel. Now if we look at A, B, C, and D, we are comparing the distance from the ground and the time elapsed. Well, when you are on a Ferris wheel, you get on, okay, so you're first close to the ground, and then as time passes, you get higher and higher, so your distance increases. And then as time passes, as you get to the top of the Ferris wheel, you come back down, and your distance decreases. And then it repeats and repeats and repeats and it repeats. You go back up, your distance increases, You go back down, your distance decreases. Now let's see what happens in these graphs. So part A, doesn't even make sense because you go forward and then you go backwards in time. It is not possible to go backwards in time. So let's get rid of A. Same thing on D. Even though it looks like a Ferris wheel, it is telling me I get to go backwards in time. And that is impossible, my friends. Now, A, B, and C are pretty close, but notice on C, the distance changes. Now, unless your Ferris wheel starts shrinking, the distance from the ground will stay the same the whole time. So that leaves us with B. Now, notice the strategy we're using here. We have got to look at the labels on your graph before you break down the problem, because you want to know what you're thinking about. Let's try that again on the next one. 15. The woman climbs a hill at a steady pace, and then she starts to run down one side. Your graphs are all speed and time, so we need to think about speed. A woman climbs a hill at a steady pace. So this tells me she has a constant speed. And then she starts to run down one side. If I'm running, that tells me my speed is increasing. Well, if I look at these answer choices, B is not constant at the beginning, neither is C or D. So that leaves me with A. All right, last one. Water is boiled and then allowed to sit at room temperature. And here we're comparing temperature and time. So when water is boiling, the temperature increases, and then it's allowed to sit at room temperature. So this tells me my temperature will decrease to a certain temperature. Not forever, but to room temperature. So let's look at our answer choices. A is out. The temperature is not increasing here. C is out. The temperature goes up and then it just stays flat, but we know our temperature goes down. So that leaves us with B and D. Now we have to think about this. When you boil water, that water is going to get hot, hot, hot pretty fast. And then once you take it off, it's going to slowly cool. So D doesn't make sense because this would be like boiling it and then putting it in the freezer. Because this would be like making it really, really hot and then really, really cold at the same rate. But we don't do that. We make it really, really hot and then we let it slowly cool. So that leaves us with B. Great. I hope this was helpful to you. You are now ready to do your post-assessment.